Hi guys. All right, in today's lesson we're going to be talking about the big three kinematic equations. Basically, this is anytime you have an object that's either moving with constant velocity or constant acceleration, there's a few different formulas that we're going to be able to use to make some predictions about its motion. All right. So, one of the first one of the first formulas that we've already learned is one for the average velocity of an object. So that's simply going to be the velocity is going to be the change in the distance of an object divided by the change in the time of an object. Right. Now keep in mind, this formula only gives us the average velocity. All right, so this is really useful if it's an object that's moving with constant velocity, like our constant velocity buggies, or a person walking, or just figuring out, right, like a plane speed from point A to point B. One thing we also learned is that there's a second formula we can use, which would be, I'm going to use this little bar here. So the V with the bar over simply indicates that it's the average. All right, so it's going to be equal to the final velocity plus the initial velocity divided by 2. All right. In our acceleration lesson, you guys learned a few different variables that we're going to find here. Now, you'll see a few different symbols being used, and you can kind of use them interchangeably a little bit. So VF can also be shown as V, right? And this is going to be the final velocity of an object. So VI, which can also be indicated as VO. This is the initial velocity. All right, so it's either VI, which stands for initial, or VO, which is going to be the velocity at time 0. So again, you'll use these symbols, you'll see these symbols kind of used interchangeably. All right, and then A is just going to be acceleration. D is going to be our displacement. Right, so just kind of our change in distance. And T is time. Now keep in mind that these first four are all vectors. So you decide so basically you decide positive or negative. Right, because again, velocity vectors, displacement vectors, whether objects moving forwards or backwards, that's all a matter of perspective. So you kind of decide if that's moving in the positive direction or the negative direction. Whereas time is a scalar. Excuse me. Right. Time doesn't have a direction. It only moves one way. Right. So there's a few different equations that were introduced in our acceleration lesson. We're just going to kind of go over them and practice them here. So this is kind of assuming objects are moving with constant velocity, constant acceleration, right? So they're speeding up or they're slowing down. So first, we have an equation that will allow us to solve for final velocity. It would be the initial velocity plus acceleration times time. Now again, this is essentially just a linear pattern. So, what's going to be helpful for all of you guys is for each of these types of problems, because this gets a little bit mathy, is set up a little chart for yourself. All right, well, it's going to seem pretty mathy. Once we kind of break it down, it's all going to be very basic very basic algebra. Right? So first thing you want to do is just kind of figure out what do we know and start inputting it into the correct spots. So we have a car that's traveling 7 meters per second, and it speeds up to 22 in 1.7 seconds. What's the acceleration? Okay, so we're just doing some inputting here. So first things first, we're given the final velocity, which is 22. Right? I know that because that's how fast it's going at the end of the story. I know the initial velocity. I know the time. I'm trying to find the acceleration. And I don't need and don't have the displacement. So I'm just going to cross it out for now, just to kind of clear things up. All right. So first things first. I have my equation. Now there's two different ways to kind of go about this. And this is going to kind of be based on your level of comfort with algebraic functions. So the first method is you simply do what we call plug and chug. Okay. Now that we have some values for these different variables, you can just simply input them. Right? We know that our value for final velocity is 22. For initial velocity, it is 7. For acceleration, we don't know that. But we do know time. All right, and then from here, we just do some basic algebra. All right, so I'm just going to subtract 7 from both sides. I end up with 15 equals 1.7 a, and then divide both sides by 1.7, and then a equals 8.8 meters per second squared. Now, another method you could do is do it a little bit more algebraically. Right? So we have our equation. You know that you're solving for a. Right? So you could do is start by just rearranging your equation. Right? So we subtract VO from both sides. All right, and then next I'll write that. So I get V minus VO equals A times T, and divide T by both sides. And then I get V minus VO divided by T equals A. Which again is a formula that we actually used in our acceleration lesson. And now, when you plug it all in, you actually don't have to do that much algebra, right? Because you already have the variable you're looking for isolated, which would be acceleration. So, again, whatever's easier, you can just plug all your numbers in from the start, or rearrange your equation to solve for your variable, and then plug in your numbers and solve. Okay, let's take a look at another equation here. This is going to be an equation to solve for displacement. Now this is going to be the initial velocity times time plus 1/2 acceleration times square. Now once again, if you look closely at this formula, what we're essentially seeing is that this is going to be a quadratic formula, because in this case our x variable is time and it is squared. And there's also a y-intercept, right? It's considering how fast is it be going initially and for how long. All right, so just know that in this case, if an object is accelerating, we know its displacement is going to be moving quadratically or changing quadratically. All right, so same thing here, right? We set up our chart. All right, so V, VO, A, D, T. All right, starting from rest. Okay, chart was 40 meters. What's the average acceleration? All right, interesting. All right, so we're given here is we know that the sprinter starts from rest. So they're starting from 0. So at time 0, right, their initial velocity is 0. Now, this is going to make this equation a lot more manageable, and you'll see why here in a sec. Right? We're also going to see that their motion happened all in about 4.82 seconds. Then we can see that they moved 40 meters. We're trying to find their acceleration. We don't need and don't know their final velocity. Now again, for this particular problem, we don't need the final velocity, but we could always use another equation to solve for it. Anyways, so like I mentioned, a couple of different ways to go about this. You can simply rearrange your equation algebraically and then plug in chug, or you can plug in chug from the beginning. All right, but one important thing to notice, and you'll see this a lot. All right, so this is our equation. Now, anytime you're using this equation and the initial velocity is 0, that's always going to be super helpful, because that essentially means that this whole part of the formula, which is essentially your y-intercept, is eliminated, right? Because you're just starting from 0, right? There's no head start. So then you're left with d equals 1/2 at squared. And this is going to be far more manageable. So again, you could rearrange this whole equation, right? Multiply both sides by 2, divide both sides by times squared, or you can just go ahead and plug in your numbers now. You know, both methods are going to work. You do you. So just kind of simplify here. I'm just going to plug in some numbers, right? 1/2. I don't know A. Again, I'm only squaring the time. I'm not squaring the entire equation there. You can just go ahead and solve this here like this. Alternatively, for me, I actually prefer rearranging my equations like this. Okay. Go ahead and multiply both sides by 2. And so I get 2d equals at squared. Divide both sides by t squared. Okay. A equals 2d over t squared, which is going to equal 2 times 40 divided by 4.82 squared. Calculate this up. A equals 80 divided by 23.23 is going to equal 3.44 meters per second squared. All right. Now, finally, we have an equation that will give us the final velocity. Yes, another equation that will give us final velocity. This one's going to be final velocity squared equals initial velocity squared plus 2 times the acceleration times displacement. All right. So, what we're going to see here is we're going to see an equation that on its surface looks a little bit complicated, right? Just because we're squaring a couple different variables. But again, this one's actually one of the easier ones to use. You'll notice in this one, we don't have time. So this would be an effective formula to use when you're not given and don't need to find time. So I'm going to just set up my equation variables here. And that's something I should have mentioned, right? In this one, this is a good equation to use when you don't know displacement. This is a good one to use when you don't know and don't need final velocity. This is a good one to use when you don't know and don't need time, right? Okay, so our final velocity here is how far travel reaches 30 meters. So this would be 30 kilometers per hour. Okay. Let's start at 15 kilometers per hour. Okay, and we know the acceleration. And we're trying to find this displacement. So we don't know, don't need time. Now, keep in mind, for all of these, you always want to do conversions back into our SI units. Basically our standard units. So we're given the velocity in kilometers per hour in order to kind of figure this out, especially because we're trying to figure out how far it went in meters. I guess we could find it how far it went in kilometers, but this is honestly going to be easier. We want to convert kilometers per hour back into meters per second. Now, we can do a whole lesson on dimensional analysis, but just as a very quick thing, this is something that's worth memorizing. If you're converting from kilometers per hour to meters per second, all you need to do is just divide it by 3.6. And we can get into the why, right? This is essentially just thinking about how many meters are in a kilometer, divided by how many seconds are in an hour. And we're going to be left with a final velocity of 8.33 and initial velocity of about 4.167. All right, so in this case, I'm trying to find the displacement here. Again, because I don't know the time, don't need the time, I'm going to go with this equation. So again, I'm going to try to isolate my displacement variable. So I'm going to subtract VO squared from both sides. Again, I'm subtracting it, not dividing it, right? Because we're simply adding it onto the equation. We have V squared minus VO squared equals 2A times displacement, and now I can divide both sides by 2A, which gives me V squared minus VO squared divided by 2A equals my displacement. And then now I can just do a little bit of plugging and chugging. All right, so that's going to give me 8.33 squared minus 4.167 squared divided by 2 times 2 is going to give me about 13 meters. So again, you could have just plugged it all in from the beginning and solved. I actually find it's less math to do it this way, but you do whatever you're comfortable with. All right, there's a few more example problems here. In Canvas, there's an answer key, so you can actually try these out on your own, and then you can refer back to that answer key to kind of see how you did. And then there's a worksheet that you can then go ahead and solve as well.